Let's continue in the second half. I want to give some examples of linear maps. So first one, let us fix K be arbitrary field. When a specific field is considered, then I will mention it that time. So D, let's take, let D be any subset, be any set, and consider the vector space V equal to K power D. Remember, K power D is all K valued functions on the set D. Is the set of all K valued maps on D, and our addition is component wise, scalar multiplication is also component wise. And let us fix some T naught in D, and let us look at the map K power D to K. So given any function x, I will call the functions to be x now. X is a function from D to K, and I evaluate this function at this given T naught. So this goes to x of T naught. X of T naught is an element in K because x are K valued. So this is a evaluation map at T naught. That is the reason I denote it by epsilon suffix T naught. This is evaluation map at T naught. Want to check that this map is a K linear map. It is epsilon T is K linear. So what do we have to check? That means we have to check that if we are given two functions x and y in KD, epsilon T0 of x plus y equal to epsilon T0 x plus epsilon T0 y. We have to check this. But what is this? This is the function x plus y is evaluated at T naught by definition of epsilon T naught, x plus y evaluated at T naught. But the definition of addition of functions is pointwise, which is same as component wise. This is same as x at T naught plus y at T naught. But x at T naught is by definition epsilon T naught at x, and this is epsilon T naught at y. So we have checked this. So we have checked that this is K linear, and because the values are in K, it's actually K linear form on K power D. So there are many K linear forms in this case. When you vary T naught in D, at each T naught you will get linear form. So actually you have a map from D to K linear forms on D, KD, that is, if you remember our notation, K power D star. This is by definition home K power D K. So T going to epsilon T. This is a map. So there is a big flow of linear forms on K power D. This is very useful for studying a vector space. When there are many linear forms, we can use these linear forms to study a vector space better. Okay. So next thing I want to compute what is the kernel of epsilon T naught. So this means this is all those functions x in k power d which go to 0 under epsilon t naught. This is precisely the kernel of this map. And what is this condition? This is precisely means x at t naught is 0. So the kernel is precisely all functions, k valued functions on D which vanish at t naught. Usually such considerations are done in analysis courses to study functions and so on. So this language of linear algebra will help tremendously studying analysis. Also the next example will tell you this more. So for example, now let us take the field K to be the field of real numbers R, and let us take I to be the interval. When I say interval, that could mean open interval or closed interval or half open, half closed and so on. But this typically interval means a comma b, where a and b are real numbers and a is less than b. So this interval has enough points. Okay, and then what vector spaces are we considering? One vector space we consider is C, R, 0 and I. So what is this? This is the space of continuous functions. Functions real valued on the interval I, R valued. And nothing special about field of real numbers wherever the continuity makes sense. So for instance, I could have taken C, complex numbers, but for illustration I am fixing it the real numbers. Strictly speaking, I should have written this capital, this standard notation which I had used earlier, double line K is either R or even C. But let me stick to real value. Alright. So this is, we have seen that this is a vector space. This is just because one learns, when you learn continuity, one learns that if you have two continuous functions, then the sum, which is pointwise sum, which is also component wise sum, this is again continuous functions. And a scalar multiple of a continuous function is again continuous function. All this one learns in a first course analysis. This is a subspace of R power I. So big vector space is R power I, and this is a subspace there. Another subspace here is, if you remember, when I did examples of subspaces, now continuous, more than continuous, C1 functions, C1 Ri. That means continuously differentiable functions. Functions on I, real valued, R valued. Again, this is a subspace because two continuously differentiable functions, their sum is continuously differentiable, their scalar multiplication is continuously differentiable, and derivative of such function is done by some wise. So I will just say it in a minute. And continuously means they are differentiable and the derivative is also continuous. So we have a natural map here, namely, let me write it capital D. Capital D is for differentiation. So what is the map D? Given any function phi, map it to d dt of phi, which also one denotes by different disciplines in science or engineering, they denote in a different way. For example, I have seen the notation like this, phi upper dot t, upper dot, this is the differentiation of phi, or phi dash, or of course d dt, and I am going to use it d of phi. So this is a map, and obviously if phi is continuously differentiable, then the derivative is a continuous function. So therefore this D is indeed a map from C1 Ri to C0 Ri, and I want to say that this map is a linear map. D is K linear. What does that mean? That means we need to check that D of A phi plus B psi equal to A d phi plus B d psi. But these are the usual standard rules of differentiation that one learns in a first course on differential calculus. Okay. So another, it's K linear. Another thing is D is surjective. What does that mean? That means given any continuous function, there is a continuously differentiable function whose derivative is the given function. So this is precisely the existence of a primitive function for continuous functions. This means given any continuous functions, there is a function which is called a primitive function, namely in some people also call it integral. So that the fundamental theorem says that integral of phi exists, and the derivative of this integrated function is precisely the given function phi. This is also known as fundamental theorem of calculus. If you see the history, between the derivative and integration, who came first is actually the integration came first because of the need. Derivative come later, and the beauty of this theorem is those concept came much different time, but they are finally connected with this nice equality, which is therefore it is called fundamental theorem of calculus. Okay. And surjective is existence of primitive. Now continuing the next example. Okay, continue. Now I want to give a map in the other direction. The map in the other direction is, that is C from the continuous functions on an interval I, real valued, to C1 functions on I. There is also a natural map here, namely the integration. Any continuous function phi, you want to map it to its integral. So that operator, this integral operator I will denote by S. S is evolved from integration, and the integration evolved from the sum. So the sum, when you become smooth, that becomes this sign, integration, and then for our English purpose, for our operator purpose, it is denoted by S. So this is the function. Now it should be a function. Which function is it? That function. Okay, let me get, so this is the integral phi. You should think as a map from T I to R. So this is the map, T going to integration from a T naught to T phi T dt. Actually, strictly speaking, I should use the different letter, but it's okay. So this goes to, let me be more precise. So this is phi to tau, tau d tau. After some time, I will also explain you why this d tau is written here. So this is a map, and now what is the, just now what the fundamental theorem I said was, if you look at decompose S, see the D operator was here and then compose with S, that is nothing but the identity operator on C0 Rk. And what is the operator? The other composition also makes sense. S compose D is precisely the operator which sends the map F, map phi to the map phi minus phi evaluated at T naught, where T naught was fixed. T naught is fixed in the interval I. This is because the function doesn't determine the integral uniquely, but it's determined up to a constant, and that constant is uniquely determined if you evaluate at a given point. So that is why this phi at t naught. So also from this equality it is clear this D is surjective. See, because decompose S is identity, so D is surjective is clear from here. D is surjective is clear, also S is injective is clear, but they are not isomorphisms. Okay. Okay. Another extension, or let me write the number 3 again. Now let us take R vector space of real valued continuous functions, let us say on a closed interval a b. And if you look at the integral, definite integral, so this is my vector space. From here to R, there is this operator integral a to b. Any function phi goes to the integral a to b phi t dt. This is actually a constant. This is a real number. Integration, a definite integral is a real number. Which real number? That is phi b minus phi a. This is a real number. And the properties of integral that we study, that say that this operator is a linear operator. So properties of integral transfer to this of definite integral shows that this operator is R linear form on this vector space of continuously valued functions on the closed interval. So there are many linear forms. This integration is one of them, and that is why studying analysis is important, and nothing special about the closed interval. One could have taken arbitrary topological space actually, and could have done this in a more generality. Okay, so that's enough for this. Now let me take up another very important example, which is the heart of this course. So another example is what is called linear system of equations. What I want to show in this example is studying a linear system of equations is equivalent to studying linear maps, and it is better to study linear maps than linear system of equations, and that is much more general and much more easier. So let us fix a k is a field, and my vector space is now k power n, and W is k power m. M and n are two natural numbers. Remember, this also is same as, either you can think the elements of V as n tuples, or you can also think them as functions from 1 to n to k. These also are functions from 1 to m to k, or m tuples, whichever. This is also still these vector spaces are given with a basis. The basis is also fixed here. When you have written V equal to k power n, the standard basis is also fixed. So the standard basis here is E1 to En. But here the standard basis here, now I cannot denote E1 to En because there will be confusion, right? These are n tuples and these are m tuples. So whenever I want to use standard basis of W, I will be careful and not use E1 to En. Otherwise, there will be confusion. And let us look at the map F, K linear map. F from k power n to kn. I will show you such a linear map will give rise to a linear system, and then we will analyze what does one mean by solutions of linear systems, and how do you decide in terms of these linear maps they are consistent and so on and so on. Okay. So, this linear map is given, that means given any x here, it goes to fx. Remember, if x is a tuple x1 to xn, and this x1 to xn, they are components of this x, they are precisely the coordinates of this vector x with respect to the standard basis. So, this is also written as x1 e1 plus xn en. So, these coordinates are uniquely determined by this basis, that is what we have been noting earlier. So, now where will this go? So, f of x is therefore f of x1 e1 plus xn en. But f of this, because f is linear, this is same as x1 is a scalar. So, x1 will come out f of x1 e1 plus xn f of en. So, this means this map f is uniquely determined. So, f is uniquely determined by its values f of e1, f of en, which are vectors in k power m. So, they are m tuples. Okay. So, let us analyze what are. So, therefore, I want to write this f of e1, f of en, they are m tuples. So, I want to write them. So, let f of e1 is a vector in k power m. So, it has m components. So, therefore, I can write this as a1 1, a12, a1m. So, this again, this representation we have used a standard basis of k power m to write this, and these a11, a12, a1m are the coordinates of f of e1 with respect to the standard basis of k power m. So, in general, for any j in 1 to n, we have f of ej equal to a1j, a2j, amj. They are m tuples. They should be in k power m, and they should depend on the j. That's it. Yes? No. This has m entries. This has m components because they are in k power m. Okay. So, now if you look at the equation f of x for any x in k power n, f of x is some y is in k power m. So, now instead of denoting the standard basis as rows, I want to denote it as a column. So, this one will be what I want to compare the elements of k power n and k power m. Instead of writing row vectors, I am writing it as a column vectors. So, f of x has as a column, what are the entries we know? That is, what do I have to do? I have to take this x which is x1 to xn, and then I take x1 and then e1 and so on. So, when I compare the components for each I from 1 to m What do I get here? Here I will get y1 on one side, that is the first component, first coordinate of y with respect to the standard basis of k power m. On the other hand, what will it be? It will be a11 first component of e1 times x1, that is a11 times x1 plus a12 times x2 plus a1 n times xn. That is the first component of f of x. Remember, because this f of vj we are thinking as a column vector. So, the first component will be a1j times x1, a2j times x2 and so on. So, in general the mth component will be ym on one side, the other side it will be am1 x1 plus am2 x2 plus amn xn. So, which is indeed looks like a system of linear equations. There are m equations in n unknowns. So, the problem is to find, given y, you want to find x. So, that means we want to solve this equation. Given y, we want to solve how many x are there with this condition. So, that is precisely, so what are we looking for? We are looking for given y, fix y in k power m. We are looking for all those x in k power n such that f of x equal to y. So, this is nothing but f inverse of y, the fiber of f over y. And the system being consistent is equivalent to saying the fiber being non-empty. Whenever fiber is non-empty, there will be some x in that, and that x will be a solution of that system.
There is a problem with the index. No, that's fine. He is taking column vectors.
We are taking column vectors. All right. So, let us do it little bit more so that it will become more and more clear. So, therefore, the problem is the following. So, let us, to be consistent with the earlier notation, given B and think of B as a column, B1 to Bm, this is given in k power m. We want to decide when exactly the fiber f inverse B, which is by definition all those vectors x in k power n such that f of x equal to B is non-empty. In the language of system of linear equation language, this means the system f x equal to B is consistent. That is equivalent to saying the fiber is non-empty. You see, also it is very neat and we have to write much less. The writing is less and the confusion is also less. So, we want to decide that. So, now note what is the image F. Remember, image F is a subspace of k power m. Which subspace? This is f of v, f of k power n. But k power n we know E1 to En is a basis, is a k basis. That is, k power n is generated by this in particular. Therefore, the image will be generated by the images of this. So, image of f is generated by the vectors f of E1, f of En. In our earlier writing, this means we were writing like this: image of f equal to k f E1 plus k f E2 plus k f En. This was precisely the meaning of a subspace being generated by these vectors. This is the smallest subspace which contain all these vectors. Okay. So now the question becomes, therefore, so F inverse B is non-empty if and only if there exists x in k power n with f of x equal to b, because such a x will be in the fiber of b. But that is if and only if this b belong to the image of f. But image of f, we know it is generated by f E1 plus f En. If this b belongs here, that is equivalent to saying the two subspaces generated by f of E1 to En and f of E1 plus f of kf E1 En plus kb. If I add this b to the generating system, it will still generate. So that is the meaning of this is equal. This inclusion is obvious. What is more important is this b belongs to this set. But how do you check this? Just by using one click. That is equivalent to saying their dimensions are equal. So dimension of the subspace kf E1 plus kf En, this dimension of this subspace equal to dimension of the subspace generated by f E1 plus kf En plus kb. So this is very good. You just have to check the dimensions are equal. So I will formally note this example shows that the study of finitely many linear equations in finitely many unknowns is or can be reduced to study linear maps between finite dimensional vector spaces. K vector spaces. Especially their image space, images, kernels, their dimensions, and more invariants, which we will introduce in the due course of these lectures. So, with this I will stop this lecture and we will continue next time. Thank you.